the organizers for giving me the opportunity to present our work in Misha Lukin's group. So today I'll talk about doing quantum optics with color centers in diamond. And in particular, I'll be talking about a new type of color center that we started investigating in the last year in Misha Lukin's group at Harvard. So realizing efficient single atom-photon interfaces is a long-standing goal in the AMO community. And realizing such a device would open up applications such as realizing quantum networks or all optical information processing devices. And there's already existing platforms that are doing a very good job in this direction. One of them is the all-solid-state approach, which we also heard about a lot about in this workshop, and that involves using quantum dots coupled to coupled quantum dots to nanophotonic structure, using quantum dots that are coupled to nanophotonic structures. And this system has a number of advantages. In particular, it has very strong interactions. So atom-photon coupling can be very large, and the timescales in the problems are on the order of tens of picoseconds, so it's very high bandwidth. And these quantum dots are naturally trapped atoms, so they remain confined within the cavity without any effort to trap them. And what's also really exciting is that this is a developed material system. So you can do fabrication and create multiple such devices on a single chip. But there are also some challenges. If you really want to couple multiple quantum emitters with one another, there are challenges associated with the random positioning of such devices, for instance, as a consequence of the self-assembly process. And there's also a very large inhomogeneous distribution on the order of tens of nanometers, so the emitters are not resonant with one another. And then there are artifacts from the solid-state environment, namely spectral diffusion and short coherence in such systems. And on the other side of the spectrum, there's the atomic physics approach, and there's been a tremendous progress in the last years in coupling atomic systems with nanophotonic structures, in a way combining best of both worlds, where you have the atomic coherences and then large cooperativities, large interaction strengths associated with nanophotonic structures. But there are still technical challenges associated with trapping these systems. Therefore, it's still meaningful to ask whether we can combine best of the atomic physics approach and this solid-state device approach. And one relevant question is whether we can find quantum emitters that are really atom-like, in the sense that they have long coherences and narrow inhomogeneous distribution. So with that, I'd like to introduce a color center in diamond, which addresses a lot of these challenges that are typically considered standard and maybe unavoidable for solid state, and it turns out this is not the case. So the Silicon-Vacancy center has a number of properties that are important for quantum optics applications. Mainly, they have optical coherences which are protected by their inversion symmetry, and this effectively isolates the optical transitions from the solid-state environment, and this results in a very narrow inhomogeneous distribution as well as suppressed spectral diffusion. And like the nitrogen vacancy center you have heard of probably before, it has electronic and nuclear spin degrees of freedom, which you can use and manipulate using optical transitions. But also from a device point of view, it's also important to ask, can we deterministically place multiple of these atoms in nanophotonic structures? And it turns out this is possible with the Silicon-Vacancy center, and you can deterministically position emitters. And there's an existing nanophotonic platform made out of diamonds. So in the talk, I'll quickly go over all these properties. But just as a general introduction, color centers in diamond are a unique system, and they're nature's trapped ions. So for instance, the nitrogen vacancy center is a famous example. And this one consists of a substitution nitrogen with a vacancy. These two combined, they effectively make up a molecule in diamond. And it has this remarkable property that you can achieve long spin coherences even at room temperature. So this is great for spin physics. But for doing quantum optics, it has a number of challenges. Mainly, the two biggest challenges are the fact that the coherent part of the emission is only about 4%. So only 4% of the photons result in a resonant cross-section. And also, within this zero phonon line by itself, also undergoes spectral diffusion. So the transition frequency of the zero phonon line is sensitive to the solid state environment and the fluctuations in the environment as well. It turns out the Silicon-Vacancy Center addresses both of these questions, both of these challenges. First one was the zero phonon line, and for the Silicon-Vacancy, most of the emission is into the zero phonon line. So most of the photons that are emitted are useful photons that have narrow line width. And spectral diffusion is suppressed by about 2 orders of magnitude, and I'll explain the physical origin of this in the next slide. And similarly, they also exhibit a very narrow inhomogeneous distribution, which is also important for practical applications. So what is the origin of this superior optical properties? It's actually very simple to understand. So this is what the molecular structure of the Silicon-Vacancy Center in diamond looks like. Unlike the nitrogen vacancy center, this system has inversion symmetry. So the system consists of an interstitial silicon atom that's sitting between 2 vacancies. And the silicon constitutes an inversion center for the system. And in general, in the solid state, the spectral diffusion is caused by these fluctuating charges in the environment. And the way they couple to the optical transition frequencies is via the DC Stark shift. And if you're looking at a quantum emitter in the solid state, typically you have a permanent dipole moment because there's no spherical symmetry for these systems. But if you can identify a quantum emitter that has inversion symmetry, then the orbital states are going to be parity eigenstates with vanishing permanent dipole moments. And all of a sudden, you can cancel out this linear DC Stark component. And typically for quantum dots and NV centers, this term is finite, meaning that you have linear sensitivity to the electric field environment in the crystal. So what this symmetry implies is that the transition frequencies are insensitive to electric fields, which results in reduced sensitivity to the solid state environment, and this gives rise to the suppression of spectral diffusion phenomena. It allows transform-limited optical transitions and very narrow inhomogeneous distribution. So I'd like to quantify these just a little bit based on measurements we did in the last year. So just as a definition, what I mean by inhomogeneous distribution is the spread of optical transition frequencies between different emitters. And we probed this in an experiment where we did an experiment where we shined a narrow excitation laser. So this laser had a bandwidth of about 10 megahertz, line width of about 10 megahertz or so. And then we scanned this laser across the diamond sample. So here we're scanning over a 100 micron square area. And then we collected fluorescence coming out of these quantum emitters. And what you can see here is that within the bandwidth of our laser excitation, which is 10 megahertz or so, we can address a high density of resonant emitters within the line width of this emitter. So the spots you're seeing here are individual silicon vacancy centers. And to get a sense of the distribution, we repeated this imaging protocol at laser detunings of about 500 megahertz. And then once we go to a detuning of about 1 gigahertz, you see that the density of these emitters goes down quite drastically. And for the solid state, this is really... That's strange. No, that's not it. Okay, let's recouple. Yeah, it seems okay over here.
Jim, can you?
Have to go through all slides.
So how does this 1 gigahertz compare to the NV case?
So there, I mean, if we compare it, the NV is more like tens of gigahertz. Yeah. So there are a few so there are multiple components that go into this inhomogeneous distribution. One of them is the electrostatic distribution of the
I switch the input.
The detector is working.
I see. Okay. Is there another laptop maybe? I could try the HDMI.
Can't stop thinking about it. So as you walk in,
Okay.
Yeah, we could try, certainly. That's not good.
So it went dark suddenly.
As you were connected.
No,
Yeah.
I mean, just during the talk.
Yeah.
So it went before.
You do have HDMI.
Yeah.
Can we use?
To try it earlier on the others that HDMI was giving them an issue. And when you disconnect.
Yeah,
does it do like a
Yeah, it does the screen refreshing.
Does this help or police?
Is it just the ITAMP tab?
Let's just try this as well. It might be slightly out of date, but sure. Let's just try this. Okay. Okay. Oh, come on. Well, let's try this. Oh, okay. All right. Sorry about that. I have no idea what that was. Okay, so the ratio of this inhomogeneous distribution, the figure of merit is how it compares to the radiative line width or the lifetime limited line width. And here this ratio is about a factor of 10. So that means if you picked out two random emitters in a sample like this, there's a high probability that they'll be nearly resonant with one another. And it also means that you can generate, you can find many spectrally indistinguishable emitters, millions of them on a single diamond chip. And indeed, that's what we did. So we looked at the sample and picked out two emitters that were nearly resonant with one another. And we looked to see how indistinguishable the photons they emit are. And to do that, we tested this by using a Hongao-Mandel interferometer. And we got a visibility of about 70% or so, which was mainly limited by the detector timing responses in this case. So next, I focus on, well, I guess, how much time did we lose? 5 minutes?
You have about 15 minutes.
Okay. Right. So next, I'll focus on the spin properties of the system and talk about how we can access memories, spin memories here. So I'll give a quick overview of the electronic structure of this defect. So in the ground states, you have two degenerate orbitals, and these orbitals are some linear combinations of the dangling bonds coming out of the carbon. So these are really local orbital states. And these two degenerate orbitals are occupied by a spin 1/2 particle. And this means that you have a fourfold degeneracy in the ground states. And the spin-orbit interaction, there's a spin degree of freedom and an orbital degree of freedom, and these are split by the spin-orbit interaction. And it results in a level structure that looks like the following. And at zero magnetic field, this level structure allows access to optical lambda transitions. And these optical transitions at zero magnetic field are spin conserving. So if you're driving a transition, you're not changing your spin degree of freedom. But if you apply an off-axis magnetic field, you break the symmetry of the system, and this allows the forbidden transitions. This allows the cross transitions between different spin states. But also, there's one more degree of freedom that we can couple to, and this is the nuclear spin degree of freedom. So if we work with the 29 silicon isotope that has a nuclear spin of 1/2, and this gives us an additional qubit, the nuclear qubit, that couples to the electronic spin degree of freedom via the hyperfine interaction. All right, and the good news is we can control these electronic states using all optical schemes we're familiar with from atomic physics. And for instance, in an experiment here, we showed that we can achieve a coherent population trapping between different ground state components. And in particular, we had a pump laser on the transition D, and then we scanned a probe laser on C, and we saw a resonance that's much narrower than the excite state line width of the emitter, showing that we're actually probing ground state coherences. And using such lambda systems, we can probe the ground state spin properties of the system. And it turns out at the cryogenic temperatures we're working at, the T1 time of the electron spin is about 2.4 milliseconds. And the T2 star, so the coherence rate of the electron spin degree of freedom is about 35 nanoseconds. And the way we inferred this was mainly looking at the line width of the coherent population trapping, the 2-photon resonance. So the question is, where is this 35 nanosecond timescale coming from, and whether if it is something fundamental or if we can improve this number. It turns out this relaxation is actually coming from this relaxation is coming from the interaction of the orbital degree of freedom with the phonons in the crystal. So orbitals couple to phonons very effectively, and this means that the orbital states, the orbital degrees of freedom, have a very short depolarization timescale. And the way this impacts the spin degree of freedom is via the spin-orbit interaction. So that we measured at cryogenic temperatures an orbital depolarization rate of 40 nanoseconds, and this matches very well to the dephasing rate we measured for the spin degree of freedom. But the good news is the orbital relaxation slows down dramatically as we go to lower temperatures, and the dependence is given here. This is the relaxation rate as a function of temperature. And the good news is we think we will be able to extend the spin coherence by cooling down to lower temperatures. But for that, we need to go to below 4 Kelvin. And as an estimate based on this fit, we think that the coherences of milliseconds will be achievable at 300 millikelvin. All right, but there's an alternative option if we don't have a dilution fridge, and we try to have access to a long-lived memory qubit. We can also use the nuclear spin degree of freedom in the system. As we know from previous work in NV centers, for instance, the nuclear spins in diamond can have very long coherence times on the order of second. And that's why we would like to develop a way of addressing these nuclear spin degree of freedoms. And in the coherent population trapping measurements in the EIT measurements that we did with the 29 silicon isotope, we were able to resolve the hyperfine structure, which means that we can measure the nuclear spin degree of freedom in an all-optical manner. So this allows us to potentially initialize the nuclear spin degree of freedom by measurement, and then we can do RF operations to control a long-lived memory qubit. So that's why we think the Silicon-Vacancy Center is a potential promising quantum node. In particular, it has the electron that we can use to interface with photons, and the nuclear spin, which we can use as a memory. So in the remaining 10 minutes. Good. In the remaining 10 minutes of the talk, so I've so far focused on the properties of the emitter by itself, but there's a platform that enables us to realize cavity QED physics in diamond. So in particular, there's a developed fabrication procedure that enables us to have high Q photonic crystal cavities, and there's also a very nice procedure where we can implant these silicon vacancy atoms in a desired array. So this is very important if you want to really make multiple of these things on a single device. And then finally, I'll talk about some actual cavity QED measurements where we'll do transmission measurements using these silicon vacancy centers. So we'd like to make cavities out of diamond, but there's one challenge, and it's that it's difficult and essentially impossible to grow diamond on top of another material. So you cannot grow a thin layer of single crystal diamond on top of another wafer. So this means that we don't have access to a thin substrate, and we need to achieve Z confinement in the Z direction in some way. And to do this, there was a very clever technique that was developed here at Harvard. And the approach involves the following procedure. So we start with a diamond substrate, and we use E-beam lithography to define the mask. And then we put this sample inside the Faraday cage, and then that goes into a reactive ion etcher. So using this technique, the ions coming from the plasma, they come at the sample at an angle. So this allows us to etch the sample at a particular angle of our choice that's determined by the angle of the Faraday cage itself. And this way we can achieve free suspended beams, so these could be waveguides or cavities, so that could be single-moded or can be used as cavities. And this procedure works quite well, and this is what a resulting cavity looks like. So this is an SEM image, and everything you're seeing here is made out of diamond. This is a 1D photonic crystal cavity. And the typical parameters for this cavity that we measure in the devices we fabricate are Qs of about 7,000, typically varies from 5,000 to 10,000. And the simulated mode volumes for these structures are on the order of 2 lambda cubed. We can also tune these cavities over a wide range using gas tuning. So we perform our experiments at cryogenic temperatures, so the sample is at 4 Kelvin. And for us, temperature is very critical, so because the emitters are living inside the material itself. Therefore, if we heated up the sample, it would degrade the properties of the emitter. So we don't do temperature tuning. Instead, we condense some gas, essentially depositing some gas on the cavity and changing the resonance frequency this way. And this process is very reversible and simple to implement. Now I'd like to present how we deterministically position these silicon-vacancy centers across the nanophotonic structures. The process is fairly simple. So we start with some nanophotonic structures, and in this example we have one-dimensional waveguides made out of diamond. And then we send this sample to our collaborators at Sandia National Labs, where they have a focused ion beam that can use silicon ions as a source. So this allows you to focus a silicon ion beam right wherever you want, essentially. And the resolution of this process is remarkable. The focal spot of the ion beam can be as low as 30 nanometers. So when we ask them, when we tell them, when we give them the coordinates, we know up to down to 30 nanometers where these silicon vacancy centers will be located. And for us, what we care about is what we would like to compare against is the wavelength, and this is much smaller than the wavelengths we're operating at. And also we can change the dose of implantation. So we can determine how many emitters we want to create in one spot. We can also change the depth by changing the energy of the ions as well. So this process is very, very flexible. And then we anneal these samples to activate the emitters and then heal any damage induced by the implantation process. And what we get in the end is something that looks like this. So this is the same image, the same sample. So this was the SEM image, and this is the corresponding optical image. And we see that we do indeed get silicon vacancy fluorescence right at the centers of the structures that we created. And within our optical resolution, they are really at the center. So this is quite exciting because once we fabricate one diamond chip, we can create hundreds of these cavities. And then in parallel, we can also implant an atom inside each one of the cavities. So this process is highly parallelized.
So it's a collection of atoms, so you get one at the right frequency, or you just really try for one?
So the low yield process here, so the ion implanters have very good control over the number, so they can send Fox states as implanters. But the low yield process is the conversion from the silicon to the silicon vacancy. So that happens with a probability of about 10%. So typically we're aiming for an average silicon vacancy of about 1. So we implant about 10 to 50 ions and typically get 1 or 2 atoms at the center of the cavity. This process also allows us to arbitrarily position multiple atoms inside a cavity or a waveguide structure. So if you want to, for instance, place them by lambda over 2, lambda over 4, this technology allows you to do that with good precision. Okay, so now I'd like to go to some actual measurements. Now that we have a cavity and an atom, we wanted to characterize what the Purcell enhancement is and how strongly we can couple couple atoms into the cavity modes. And when we did the Purcell measurement, we saw that the lifetime when the cavity is on resonance is about 3 times less compared with the cavity detuned from the atomic resonance. So this corresponds to a Purcell factor of about 2, or in terms of the beta parameter, this corresponds to a beta of about 60%. So this is where we are right now. But I must point out, especially in the solid state, quantifying beta by itself is not enough, because this does not take into account pure dephasing processes where the resonance is shifting around. So this just captures where the photons are going, but really does not tell us much information about the coherence of the process. So for that, we actually wanted to probe the coherence of this process. And to do that, we performed a 3-port measurement. So we sent an excitation laser at one port, and then we monitored the fluorescence coming out of the silicon-vacancy. So when we scan the laser, we see an increased fluorescence when we hit the silicon-vacancy resonance. So this is our atomic resonance. And then when we look at the transmission port, we see that there's a corresponding extinction in the transmission of the cavity. And in our experiment, this transmission extinction was about 30%. And this corresponds to a cooperativity of about 0.2. There are a few things I need to mention about the experiment. So in this experiment, we did not polarize our ground state degrees of freedom. So we were in a thermal mixture. So actually, we were only in the right state half the time. So this means that this contrast could go up to 60% if we polarized. And there was no post-selection in the process. We analyzed all the counts coming out, and it was a 100% duty cycle. So it's a very fast measurement. And I should also point out that this was the first device we fabricated, and it worked on the first device. So that's probably the most exciting thing about this. Now what we're working on is to polarize the ground state degrees of freedom and actually put the atom in the right ground state so that we couple, the photon couples to the atom. And that we expect will bring us a factor of 2 larger in transmission. And also we're wanting to improve our control over the ground state degrees of freedom. So just beyond, going beyond polarization and starting to use ground state coherences in our experiment. So this is very preliminary from a few days ago, but we can, in this experiment, we were trying to see, for instance, if we can change the response of the system when we include a control laser, for instance. And we could, for instance, do a cavity EIT using a single silicon vacancy center. And we also want to be able to arbitrarily rotate these ground state degrees of freedom. And as we're also simultaneously working on our cavity design, and we have a few number of approaches to improve our cooperativity above 1. So with all these features, I think the Silicon-Vacancy might become an exciting new platform for applications in quantum networks and nonlinear optics or quantum information processing. So just to summarize, the Silicon-Vacancy Center has surprisingly good coherences, optical coherences for the solid state. And this is enabled by its symmetry. Essentially, it's protected from the solid state environment by its symmetry. It has electronic and nuclear spin degrees of freedom that we can use as qubits, and we expect these coherences to go up to milliseconds at lower temperatures. We can create them at desired positions along waveguides, or we can create multiple SIVs inside the cavity. And with all of these features, with all of these good optical properties, we were able to see a strong extinction from a single atom in a cavity QED experiment. So with that, I'd like to thank all the people who contributed to this work. So all these experiments were carried out in Michel Lukin's group. Some of the spectroscopy work we did together with Fedor Yelesko's group at Ulm University in Germany. And the team that's been leading this effort in Misha's group is Ruffin Evans, who's a graduate student, and Denis Sukachev, who is the postdoc. Without them, we would not be able to make any of this process. And Christian is a first-year student who recently joined. With that, I'd like to thank you also for your attention.
Thank you very much. Questions?
So can you just briefly clarify this T1 time? So I mean, you have these 2 orbital states in the ground state, and they decay with this 40 nanoseconds.
Yep.
And then you have this T1 time of the spin. This was then spin in this. So between the lower 2.
So let me just open up that slide. Maybe. So just like the way the optical dipole transitions are spin conserving, at the zero field limit, phonon transitions are also spin conserving. So Yeah, so if I had to draw the transition matrix element of for the phonon, it couples this state with that state over here. So even though your orbital degree of freedom is relaxing, you're maintaining your spin polarization.
But then is this spin T1 time of 1 millisecond?
Yeah.
Was this then between the lower two spin states? Or?
So throughout that measurement, what's happening is you're going back and forth between different orbital states for the same spin. So in this experiment, I don't remember whether we were probing this or this transition, but you're spending half of your time in either one of the two.
How do you detect then the spin coherence times?
Oh, so for that we focus on, for instance, this sublevel, and then we essentially do so we
you measure the spin between the two lowest states.
Yeah,
so the
yeah,
coherence time is-
yeah. And also that is the one that is going to improve at lower temperatures, because the ground state manifold, these two states will be isolated from phonons, whereas you still have spontaneous emission from this upper branch to the lower state branch, even at 0 phonon occupation.
Well, I can comment to the introduction. So for quantum dots with electron-photon, it's natural common spectral diffusion, and had 95% emission 0.9 platform generation.
I see, okay.
Also a question, so for the emission spectrum, you talked about the 70%. It looks surprisingly broad.
So that was taken at room temperature. So at room temperature, the 0 phonon line has a width of about 1 nanometer. At cryogenic temperature, it narrows down to 100 megahertz. So that's just broadening due to acoustic phonons in the crystal.
Maybe you already mentioned it, but can you mention again the energy scales of the ground state?
Yeah, sure. So this is at 50 gigahertz, and in temperature, it's about 2 Kelvin.
And so within one manifold, with two sublevels, how far are they apart?
So it's just Zeeman splitting in that case, yeah.
So what do you expect for the top affinity, or what can you learn about that?
Yeah, so
And do you know where the atom is, for instance, relative to a node or antinode?
so we actually have a very nice set of measurements for this. We implanted a uniform density across the sample. Maybe I could just show that if I have that here. Okay. So in this experiment, we implanted silicon vacancies not using this focused ion beam technology, but instead over the entire sample at a high density. And in this experiment, what we were doing was to collect the photons in the waveguide mode, so the photons that couple to the cavity mode. And then we were scanning the pump laser. And this way, when we take an image, if we take a cross-section of how the counts in the cavity change as a function of the pump laser, we see we can resolve the overall envelope of the cavity mode. So this is a higher order resonance. This is the second order resonance. And so we tune the second order resonance to SIV resonance. And when we tune the fundamental resonance of the cavity, we see a drastic change, and we see that it's actually the fundamental mode. So it's in some ways allows you to resolve this envelope. So we have not tried to look at sub-wavelength structure. So we have not investigated the high frequency modulation, but that's also something we could look into.
And what about the copper activity? What does it imply, or what's the maximum you could expect?
Yeah, so there's a large uncertainty right now as to, based on our design, we were expecting to see a cooperativity more than 10. But, or maybe I should refer to Purcell because that's what captures these rates. So we were expecting a Purcell of more than 10 to about 20 or so. But what we got in the experiment is about 2. So there's an order of magnitude discrepancy. And the honest answer is we don't know whether this is coming from the orientation of the dipoles. So I did not mention these polarization selection rules, or whether it's whether we have a lower precision in this implantation process, or whether there are some unknown non-radiative rates. So it's some combination of those, but we don't have a handle on them yet. And this is fairly new field, so there has not been much spectroscopy work so far. We're doing spectroscopy and applications at the same time.
But it's clear that, for example, like this mode volume scale will not, the QOD will not optimize.
Yeah.
So there is a, like, even if sort of we don't figure this
Yeah.
things out. There's at least maybe an order of magnitude.
Yeah, so you can see the mode volume in this curve essentially. So the confinement is rather weak. So that's our next generation devices where the confinement will be tighter.
I think we should move on to the last talk. There's this extra talk